Another trend on the periodic table is called electronegativity. Now, this one is a little different to understand. So, what we have to realize is that electronegativity has to do with elements that are in a compound. Okay? So, it is a measure of the ability of an atom in a chemical compound to attract electrons. I tend to think of electronegativity kind of like a tug of war between two atoms, where they are both pulling on the electrons that they share. So when a chemical bond forms between two atoms, the electrons are the reason that they are bonded together. Both of the atoms are pulling on the electrons. How much difference there is in electronegativity ultimately determines whether those electrons are completely transferred from one atom to the other or if they stay shared kind of in between. Okay? So electronegativity is going to be a number that gives us a measure of how hard the atom pulls on these shared electrons. The higher the number is, the more electronegative that the atom is. What that means is that it's stronger and pulls harder on those electrons. So as we move across a period, remember that we're seeing an increase in nuclear attraction. They're pulling harder and harder and harder on their own electrons. That also means they pull very hard on shared electrons. So we see an increase in electronegativity moving from left to right across the period because of that increase in nuclear attraction. So the same reason, increase in nuclear attraction, leads to this increase in electronegativity. Going down a group, remember how we described this electron shielding before? This idea that electron layers, as they are added, actually interfere with the nucleus being able to hold on to the valence electrons. So it makes it very hard for the nucleus to hang on to valence electrons. Well, if it cannot hold on very well to its own electrons, it's certainly not going to be able to pull very hard on shared electrons. So we see the electronegativity decreasing as we go down a group because of that electron shielding. So our general trend looks something like this, and there are numerical values to electronegativity. So you can see that as we go down a group, that the number is getting smaller and smaller, generally speaking, right? Because all of those added layers of electrons are interfering with it pulling on electrons that it has itself and also making it difficult for it to pull on those shared electrons. So very, very low electronegativity numbers down here. As we move from left to right, let's just look at lithium to beryllium to boron to carbon and so on. We see the numbers going up. Again, for the same reason. They are pulling harder and harder on their own electrons, so that means if they're sharing electrons with somebody, they also are going to pull very, very hard on those. So fluorine continues to be kind of the big bully on the playground here. It is the tiniest but the mightiest. It has the highest electronegativity. Fluorine will always pull harder on shared electrons than any other element. You notice that there really are very few numbers here in the noble gases. Xenon's the only one we can even get to form a compound, and when it does, it has kind of an average electronegativity. The rest of them don't even form compounds, so they don't even have electronegativities.